do this. Okay, great. So let's get started. So thank you all today for attending this tutorial. So actually outside is pretty heavy rain, so please take care of yourself. So today I'm going to introduce our tutorial 2 of these avionics systems, and today we are going to have a brief review of some technical stuff inside of this between week 7 to week 10. So let's get started. So first of all, let me remind you a bit of those previous issues. So in the last tutorial, I introduced this kind of question, right? Related to some integrity of the system, but notice that there has some typo in here. So before we talk this as variance, but actually this one is actually a standard deviation. So do not be get confused. So this is sigma is standard deviation. So if you're talking about variance is something that have a square on top of it. So it's a bit different between them. So this is actually a standard deviation. So next time, if you come up with this kind of same question, so do not be like getting confused with before. So I'm pretty sure. So actually how to solve this question is the same. So you can check with the last time the recording of the video. So you can have a review of how to solve this question. So I will not repeat it again. So let's continue to the next part. So in the week 7, we talk about the airborne communications. So there has actually a lot of different kind of stuff, but actually a lot of stuff is actually I think it's like not that close to us. Our this like our aviation, like aircraft engineering or aviation studies. They are more like in electronic studies. So but something that you need to know is that related to us is that the wave propagation, because in your aircraft, during the aircraft operation, because we actually can receive different kinds of signals from different kinds of propagation. So you need to know is that we have, based on propagations, we can separate different kind of wave in terms of propagation. The main rules is that based on whether it is related to ionospheric, and based on whether it is being reflected by the ionospheric or it will not be reflected by the ionospheric. Due to that, we have two categories. If we receive a signal that reflected by ionospheric, of course we have the sky wave, and if it is not, and if it is in the ground, we are like attached to the surface, we call it surface wave. We have these two kind of wave, and they are actually high frequency wave. And if we have a very high frequency wave, they actually will not have this kind of reflection because of the frequency is quite high. So it will directly go through with the ionospheric, and we only have this kind of space wave. We do not have any reflections. And of course, we will also do not have this kind of like ground surface that attached to the ground. And that's all. So these three you need to remember. And the other one is actually the same. They are using the VHF, but it directly, you have the ionosphere and you directly go through it because you have the satellite. So it's directly going through it. So we have this 4 category. And yeah, for the surface wave, you need to know is that it is based on diffraction. It's not a direct propagation, because if you look at how it looks like, is that if you're going to have a direct propagation, it will be blocked by the ground, right? So it's actually not a direct propagation. It's like attached on it. And this is based on diffraction. The method is on it. But it's too complicated to explain how the physics behind there. So if you're interested, you can look some to find some YouTube video to know how diffraction occurs. So it's actually really complicated. But for easier to understanding is that something is during the signal propagation, it has been partially blocked by an object, so that we have a diffraction. It's kind of like you have a contour that's looking like this. So it's actually attached on the ground. So we call it surface wave. And on the other hand, we also have the sky wave. That sky wave means that you have the ionosphere in here, it's ion. And then in there, you have this kind of reflection, so that what we receive is actually the reflection of the wave. And of course, if you combine with the surface wave, the reflection of wave is actually only available in a certain region. And our surface wave it also has kind of limitation, only have this kind of region. So in the meantime, in the center, between these two kinds of regions, we have a gap, which is the dead zone that your aircraft cannot receive the signal. So that's the characteristics. And after other things, we introduce some properties about the wave, and then we introduce about the half wave dipole antenna. So the basic concept of here, you can go back into the detailed video we record. But the main idea is that you need to improve the efficiency and make this works so that you cannot have the full wavelengths, because if you have the full wave in here, so you will have like positive, for example, we have positive and we have negative, and they will be canceled with each other. So what we need is that we have the antenna. Yeah, we have the antenna, and then we are going to have a half wave. Like for example, like let me have some example of the, let's say we have the half wave is looking like this, so that we have like negative and positive, so that can be consist with the same sign. Yeah, so that's how it works. So but at the meantime, we also invent some of other advanced characteristics that only using quarter of the wavelengths, we're still also able to have the same of the result. This is because of this kind of like reflection characteristic. So your antenna has a rule that you need to be attached on top of the ground. You need to be very close to the ground. In here, we have the ground. So you need to attach on the ground. But this ground, it means that actually can be any of surface with the same characteristic as the ground. It can be okay. So that's why you can see some of the half wave, this quarter wave antenna is attached on the aircraft. So some of the component is serving as a ground. So the basic idea is that you have this kind of reflection. For example, you have, let me using this drawing. Yeah. Yeah, great. Okay, let's look at this one. If we have the original signal, so what we receive is that looking like this, right? We have the direct signal. This is our antenna. This is our antenna, and we have our direct signal, and we're going to be received in here. And what we have is that we actually have half of the area, or the original area. We have this kind of the power, or etc., the effects of it. This is only 50% of the original stuff, right? But because we actually have the ground is looking like here. Let me use a brighter color. Do we have other? No. Yeah, no, anyway. So we have, but we also have the reflection, right? So we have another different kinds of reflection, and the reflection will have this kind of reflection, this kind of reflection, this kind of reflection coming here. So they're actually coming from the same angle, same direction. Another half, 50% will coming from here, so that you actually receive this another part of the another 50% from the ground reflection, so that in total you can use serve as the same amount of power, but actually another half is actually based on some reflections. So that's the idea why it is able to serve only like a quarter of the wavelength. It still works. So that's the idea, the reflections characteristics. So yeah. So after that, we will also introduce something related to dB. So dB is related to the power or other stuff they're going to compare with each other. But if you directly compare in ratio, sometimes the difference is too large that it's very hard to quantify. For example, like one is only one side is only one, and another side is like 1,000, or even more, like 10,000, like hundreds of thousands or thousands of millions. Yeah, so that's the problem. So what we do is that we use dB to do so. So in dB, what we have is actually like a ratio in here, looking like this. and with a log inside. So what we have is, like, for example, in here. So even though the ratio is very large, but if you're going to be applied with a log, then it can be used with some kind of like a smaller value, smaller amount of value to indicate a very large value. And their relationship is also very different. So that it's kind of like a proper way to count the amount. So an example is that if you're going to count the loudness of the sound, they usually use dB, because the very weak sound power with the very normal sound power and the very high sound power, the difference is very large in terms of those physical parameters. So they usually use dB to do so. So, but this is the change of the value, the comparison of the value. But we also can use this kind of terms to represent an absolute value instead of only a comparison. But in here is that it expresses the ratio with a fixed reference, which what it means is that, for example, if you are going to compare with 1 volt, then what you have is something like dB volts. The reference is this. The reference means the in is there. Yeah. So if the reference value is 1 million, then it's going to be milliwatts would be this. But if you are going to direct to be like your reference value will be watts, so it will be dB watt. So something like that. Okay, so let me also have some of the practice of how to doing so. So if you are going to evaluate those electrical parameters like a voltage, like a current, and also the power or other stuff, and we can look at this kind of questions to look at how to convert those units and those terms between each other using dB and other related units. So if you are going to representing 0 dB volts across 50 resistance has this one. So what we have is let me do this. So our reference is looking like this. So what we do is that we have what we care is about the resistance, right? And also the voltage, these two. So these two is, if you look at those equations in here, so what we need to use is this one, right? This one is related to us. So what we have is to, because in here, what we care is about the power. So dBm is something that related to milliwatts, right? Milliwatts. So that is related to power. So we use this equation. So in terms of this equation, what we have is like, you write down the equation, it should be like 10 log something because you use dB something and here. And then we have this one. And what we have is to calculate the power, which is 1 and over 15. So this one should be with a power with a square because we have this one in here. So what we have is looking like this. So if you're going to calculate this value, it should be like looking like something that related to minus 17 in here. So this one should be related to minus 17 and dB watt, something like that. And dB watts need to be converted into mini watts, right? Because what we care is mini watts here. So there has the ratio between is actually 1000 from watts to mini watts. So if you look at the table, so 1000 is looking in here. Yeah. So that we actually look at the table in terms of dB, the change is 30 dB in here. So that what we do is that to convert is to plus 30 dB to this value to make it change into dBm, which is dB milliwatts. So that we add 30 to here. Because if you're going to do this things in log, it should be in dB, in the unit of dB, it should be addition or we subtract some of the value. So we have this kind at 30. So indeed, total we've got minus 17, we add 13, so we got positive 13. So that's why we got this kind of value. So that's how it works. So how about let's do other stuff also. So if we're talking about this one, this is the difference is that now it's milliwatts, which means that it's 1 multiplied by 10 to the minus of 6. So we apply with the same equation, which is 10 log with 10. And then inside here, we have this equation. So we will have the minus 6, but actually we have a square on here, and denominator should be 50, so that we will got this one. So what we have is that, yeah, it's really complicated equations. So let me find with the directly let you know the answer of it. So actually, if you're going to have a calculator, so that you will be calculated, this result will be how much? And it would be minus 136.99. So this time will become like dB watt. So this is the result of you if you're doing so. So if you further going to, because this is dB watt, you need to convert it into dB milliwatts in terms of this unit. So you need to also add 30 to them. So what you have is like minus 107 dB milliwatt. So that's the result of it. So what you need to take care is that we have a square inside of here because of this equation. So that this one, you need to always make a square of it. So it will become like 10 to the minus of 12 inside before it divided by 50. So inside here. So that's this kind of result. So let's go into the other one. The other one is 3 dB is represented by a double in power. So how to interpret it is that if you're going to like, this is actually a comparison because it's only dB. We do not have any reference. So if you talk about the comparison, it's like we have 10 log 10 with some kind of ratio. We don't know that. And it would be, this is the comparison between different two stuff. Like, let me using a better idea. It's like A to B, A compared to B. Then we will obtain, what we will obtain is 3 dB, right? In terms of this sentence. So then what we do is do a trick to make this one to keep in this side. So what we have is like this one, and we put this part into the right hand side. So what we get is that now we become like 10 to the order of 0.3, right? This is their ratio. And if we're going to calculate this one, is very, very close to 2. So what we can have is the kind of like characteristic is that anything, if they are going to compare with in terms of dB, if it is like 3 dB, it always will attenuate with a half. So half is doubling with them. It's going to be double of the power. Yeah, something like that. So in terms of comparison, so this one you can also be see inside of this table. So if you're going to look at this table, you will find 3 is in terms of this one. Yeah. So how about minus 3 dB? So it's actually basically the same. So it will be also be 50% of the power. So we use the same equation, we can calculate that. And how about 1 dB? So we can also apply with the same idea, but now we are going to talk about increase in power. So in before is that we have 10 log 10 and A compared with B is to 1 dB, that one. And then we're going to do the same trick. So A compared to B will become like 10 to the order of 0.1. So if you're going to compare with it, what we get is the value of 1.259. So this is their comparison, right? But now it means how much is increase in power. So the increment is that is to compare with the original power. So it's not like a comparison. One is in denominator, one is in the top. So that one is that what you need to know is to have like A minus B because you care about the comparison, right? So what we have in here is actually we based on this one. We know that the difference should be in 0.259. So what we hear the increment is 25.9%. So here is about the increment. So that will be a bit different. So you need to take care about the sentence, how the description it is. Okay, so let's continue with the. So actually, I will also have these solutions in here. So you can look back into the slide I shared with you on the Blackboard. They all have solutions on it. You can feel free to check with it. Yep. So after that, we actually also in this lecture, we also talk about some related to modulation. So this part is also very important to us because they are actually very useful for your engineering study, because later on, you may have some jobs that related to some sensors or some other devices. They actually going to have some signals, right? The signals is always with this kind of like modulation in order to make those signal having meanings, because only bury the signal, they do not contain information that does not that's useless, right? So they need to have some kind of information, and how to contain this information is depending on how we do this kind of modulation. So there are in the lecture I actually told like 4 different kinds of like modulation, but actually in our daily life nowadays, like 3 of them are very useful actually, will be more useful. The first one is, let's say, is AM. What you call is like amplitude modulation. So let me use another color to better. Yeah. So amplitude modulation. So that as it seems, so it's related to the amplitude. So if you're going to use this modulation, your signal's amplitude will look very different from the original signal without any information. So without any information, our signal is looking like this, right? The amplitude is talking about the width from the lowest to the maximum. So in here is this, because if there is do not contain any information, it's only the original signal, the amplitude will be always maintain the same, right? So if you have include some of the information, so your amplitude is keep changing. In here is larger and smaller and larger, right? So your amplitude is keep changing. So that means you have already modulated something in here. Your signals is a bit different and it contains something. So that's the amplitude modulation. And another one is a frequency modulation. So if you look at this one, the original signal looks like this, right? And let me see. Oh, no. This one is the upper one is the original signal. It looks like this. So the amplitude is always keep the same. The amplitude is always keep the same. So what we do is that we modulate the middle part, which is the information. Let's say this one is the information. We're going to modulate into here. So after our modulation is that we're going to make use of the parameters inside of our data, this information, to adjust something related to our original signal. And here, the adjustment is on the frequency of the original signal, which means if our information is larger, for example, on top of this part is larger, and correspondingly, we're going to make the corresponding original signal, the carrier's frequency, become also larger. So that will be, you see, in the beginning it's the same, but when we are going to be larger for the information in here, will be more intensive. They are more close to each other, so the frequency is higher. So if we are going to have a lower value, for example, in here, we have a lower value. And then what we have is a lower frequency. We make this frequency a bit lower compared to the original. So we have this one. And yeah, so that's one of it. So actually, we also have another one is we call phase modulation. So the phase modulation is like, we're going to also make use of the information to adjust the phase, so that we're going to adjust the phase a bit forward or a bit backwards compared to the original. But in terms of the signal itself, it will look something like weird. Look into the signal, it looks like this, like a flip of the signal. This is because you have a we have 100 degrees of the phase shift. So that original phase is looking like this one, and you have 100 degrees of the shift. So that if we shift 180 degrees, what we have is, let's see, this is 360, right? So in half. So if we're going to have a half, what we have is starting at this point, and what we have is like looking like this. No. My writing is a bit bad. Okay, so let's do again. So if we are going to looking at this one, so what we have is like looking like this, right? So that if you go, it's actually looking like a flip of the signal. So that if you going have this modulation, so you also have a flip of the signal. So it looks like a flip of something. So it's like phase modulation. Okay, so after that, we will also have something, other things that related to the link, the power link between the transmitter and the receiver, because in our lecture, we also have different devices that transmit signal to each other. So one very important thing is that to make this communication works, the power needs to be enough so that you can transmit to others. For example, if I'm speaking my voice in here, so it's no way that you can listen to my voice in the entrance of our poly U, right? So it's too far away. So the power is not enough to going through to there. So we need to ensure of that. So some of the question, like for example, engineering life in the future, they may ask you about the requirement of the power so that you can make this communication link. Let's look at this example, and we're going to find the required transmitter power, this one, for an aircraft at the height of this, using this kind of frequency of signal, and below is some of the information related to our receiver, the specification of our receiver, and also some of the other terms. Okay, so that's it. So we're going to calculate the requirement of the power. So first of all, we need to, this one, how to, yes, good. So first one, we need to know how long our signal is going to be transmit, right? But from here is looking like, it's looking like we only have the distance information in terms of the height of the aircraft. But actually in the previous class, in the lecture, we know that our surface is round. If our aircraft is somewhere in height of it, the communication range is actually have a certain characteristic. And this communication range characteristic is modeled by this one. We have the line of sight signal, and it needs to fulfill this kind of equation, right? So if we're going to fulfill with this equation, we have the height in here. We already know you can calculate the communication distance. So what we have is we have the distance 1.225 following with the same equation. And here we have the square of h. And we put in here is 1.225. We have the square root of the 10,000. And what we get is 122.5. But here, be careful about the unit is nautical mile. So here is nautical mile. And if you're going to calculate something that related to the speed of sound, speed of light, or other terms, they usually use meters. So they are different. So that you need to convert it into in terms of meters. So to do so is to need to be like, let me see. We need to be multiplied with the conversion in between. So the conversion is that we need to be multiplied. I remember it's like 1.825 or something. But anyway, you will find the number. So I will directly let you know it's like 226.78 87 kilometer. So during your examination, in the final examination, you will also know the conversion between different units. I will put also in there. Yeah, so the nautical mile and the kilometers, I also put it here. So after that, we're going to, this is the distance we know, right? And we also need to know about the frequency in here. And we need to know something related to the wavelengths, because if you're going to calculate the loss during the pass, so the idea is that if you're going to have the transmission, right, to, let's say this is the transmitter, this is the receiver, and we're going to transmit this signal, and we need to calculate the required power. So we need to know how much power we need in here, how much power we need in here. And what we have is that we have our power in here, and we also need to know how much power will be lost during this propagation. So that's the idea. So to do so, this is the idea. There has a lot of loss in here, but the transmitter itself will have gain, which is to increase the power a bit. And the receiver will also have another gain to also increase the power a bit so that it can receive the power. But in the meantime, in the middle, we have this propagation. During the propagation, we will have the loss because of the distance. And this one is described by the top equation, which is this one. This equation is talking about the loss. Okay, so what we are going to do is to base on this equation to calculate. So we already have the distance in D, and we also need to also have the lambda, which is the wavelength. And this one is actually related to our frequency of the signal. So we can directly calculate it. So we have the lambda, and is equals to the speed of light, because our signal is EM wave, propagates as a speed of light, and we further need to be divided with the wavelength. Oh no, with the frequency. So that's the equation. So what we have is actually like 3 to multiply by 10 to the order of 8, and we're going to divide it by this one, because we have megahertz. We need to convert it into hertz. So megahertz is related to 10 to the order of 6. So what we get is this one, and we finally will get our wavelength is 2.5 meters, you see? So this one is actually in terms of the unit of meter. So in before, we are calculating something also related to kilometer, and it's multiplied by a time of 3. So we got the meters run, right? So that's how we're going to get it. And we also already have this one, lambda, and others. So let me rearrange the nodes in here. So at this moment, we already have the distance is 226.87 kilometer. And what we have is the wavelength equals to 2.5 meters. And we calculate the loss is equals to, this is the loss, and we follow the equation. It's looking like 20 log this one, and multiply by 4 times with pi, with the distance, and divide it by the lambda. And what we get is looking like this, and we put those number in here. So I will directly write the number in here. It's 121.14 in terms of dB. So if you put the number and use calculator, you can directly get this thing. And this is kind of like a ratio during the loss. So what you have is that you need to calculate the balance in between. So let's write again of this. So in the beginning, we'll have the power of P transmission. This is the power in our transmitter. And in here, we'll also have our gain from the transmitter. Our transmitter will amplitude a bit of the signal. In the meantime, we'll have the loss in here in the middle, to like because of the transmission propagation. And then on the receiver side, we'll also have the receiver gain. And in the end, in our user side, we'll have the signal, but the signals have a certain power. So we'll have the power of receive. So what we have is to build up the equation. It's like retransmitter is equals the receive signal is equals to what? Is equal to the transmit power plus the gain. Because in here, all the units is in dB, so they are using plus and minus. So that's, we have to pass this gain from the transmitter. And because of the loss is something we reduce the power, so we're going to minus this one. And on the other hand, we'll also have another gain. So another gain is passed to here. And then what we get is this equation, right? So the problem we need to solve is to solve PT. So we rearrange the equation. We can have this one. PR. This one add with L and minus with GR. So what we get is here we will have this one minus 89. And we're going to, because it's dBm and others are dB, they are going to use minus or plus with them. And then we minus 2.1 of the gain, but we have two of them, so which is like 2.1 multiplied by 2. And what we have is also come to also have the loss. Loss is like this one, 1/4. So what we have is to calculate this equation together. So then we will got the result will be like this one multiply this one in dBm. Yeah, so that's actually, it's quite simple. It's the linkage between transmitter and receiver, and you need to calculate the power loss in here. Yep. So that's basically this kind of question. So here is the result of how to do so. So you can feel free to check with the slides I upload. They will be here. And yeah. So after that, we'll also go into some avionics systems that related to terrestrial radio navigation and landing aids. So before I doing so, so actually there have 3 ways of doing positioning. I think you need to know with it this, because this is basically a free, very useful way when you in the future you other like engineer ask you how to do navigation or other stuff. One is to base on the 2 angles, because 2 angles actually can draw 2 lines, and the intersection can give your position. As long as this 2 angle, the reference of this 2 angle, the location, the station is known, the location is known. So basically that's how ancient people, like old people doing so. We have the map and we have the lighthouse, and we know that this direction is in here, the other direction is here. Then we know the location of our ships. So usually they do, in the old times, they do this. So what we do in the flight sim is that we base on DME and VOR. So VOR is giving we at the beginning, we know the location of our station, and then we know the angle we receive the signal based on the VOR. And then we know the distance we receive by DME. And then we can also, based on this one, the angle, we can draw, we know our aircraft is on this line. And based on the distance, you know that our aircraft is actually located in here. So the basic idea of how you do it in your flight sim. So another one is that more related to satellite, because like GPS or GNSS, because for that kind of system, they know is that the location of the satellites. So what they can do is that to make the satellite have some kind of measurement between the distance between you and the satellite. So if you already have that, based on the satellite's location, you can draw a circle, and you know your location should be on this circle. And by another satellite, you can draw another circle like this. And by the third satellite, you can draw the third circle. So these 3 circles will intersect with each other, and the intersection should be our user's location. So that's a very straightforward idea. So that's the basic approach. Yeah. So after that, we will very important stuff for avionics is the VOR and DME. So you guys should already know how it works because you learn about it, and also you make use of it during your flight sim. So the basic idea is very straightforward. Is that we have some kind of like a reference signal so that it propagates signal on all directions, so everyone can receive this kind of signal. Yeah, and on the other hand, we'll also have another signal that it has directions, so that these two will have some kind of like a rules during this propagation. So the rules is that when this directional signal is pointing to the north, then the reference signal will also emit the signal, so that it will also emit the signal to everywhere. Yeah. So that they compare with the time if it's they use a clock to compare. If these two signals have no difference in time, so that you should on this location. If the signal have a certain period of time difference, so because what you have is the example is like, if you're pointing to here, this one, the reference is already emits the signal, and it's already been received by this guy in here. And later we need to wait this one, this have a turning, this signal, the turning signal. Then we're going to have some period to like 1 second. For example, this is only for example. It's 1 second, 2 seconds, and 3 seconds. Then it further reach to it finally turns to our users on this location. So that what we have is that 3 seconds of difference, right? But in terms of the regulation, they will regulate this one to another seconds. So here is only an example. So actually what they did is that they based on the difference in time to know how far away is it. Because if you are in this location, you need to use a longer time so that the angle of another signal will finally turn to your side. So after you compete for this one in 260 degree, of course, it needs further longer time. So that's based on the time to measure. Yeah. So because it's related to the time difference of time, you can also make use of the phase difference to do so. So that if the signal is receiving in the north, so because they are being received simultaneously, so the phase should be different, should be the same. Have the difference in phase is equals to 0. But if here, so in the 90 degrees, is that you have the reference signal is the same, but your turning signal, no, actually, let me see. Yeah, so actually they will have a signal, the difference of receiving the time, so that you receive later when you receive the turning, because it turns needs some time, so that the propagation will have difference. The other one may have a small, like a shift on the phase, so that this shift on the phase is able to tell you the angle of yourself. So that's the idea. So basically it's like this. This one will have a smaller phase change. And if you're going to be 180 degree, we have a full flip of the signal, because you have 180 degree of the phase change. And of course you will be there. And if you're going back into the north, then you will recover with the same phase. So that's the idea. And yeah, we also introduced something that related to NDB and using ADF for this one. And what you need to know is that on our aircraft, we will have this kind of like antenna. And this antenna is to receive the signal simultaneously on two sides, because they have this design structure, these two parts. And these two parts will receive the signal. And if you have a certain angle and this signal, the propagation length will be slightly different. And so that you measure the difference in terms of phase, so that you know the orientation of your aircraft. So that's the idea. Okay. So after that, we'll also have the DME, the other one you very familiar with your flight sim. And what they do is that you need to remember they will have this kind of interrogation. So the interrogation is also need to be remembered is like it's a random spacing. So it's kind of like a random signal to have some of the random coding on it, and then it propagates to from our ground station and then it to our aircraft. Yeah, no, it's actually emits from our aircraft and then we further to our station and going to be reflect again, and then we're going not reflect, is to process a bit and then with another frequency, and then we're going to have it back to our aircraft, so that those information is displayed on our aircraft, so that because this kind of indicator is on our aircraft based on our being seen by our pilot. So that's the idea. So this one is on here. So the way is that we firstly from our aircraft and go to this station and going to be get it back finally to our aircraft. And the other one is like the SSR, which is the secondary surveillance radar. That one is opposite one. The guy that having the indication is on the ground, so that it starts from, for the SSR, it starts from the ground and going to the aircraft and then going back and finally receive on the ground. So they are different. And yeah, that's the basic idea. So to calculate it, it's also very simple. Is that based on the time difference also, because from the signal in here, when the signal is being transmitted from the aircraft, we have T1. And when our signal is going to be received by the ground, we'll have T2, right? And the time we are going to process the signal is T3, and then we're going to transmit the signal from our station, and being further received by our aircraft is T4, right? So what we have is like looking like this. Yeah, let's do not look at this one. What we look is like this. But if we're going to calculate the range information, is that our range is equals to, because in here we have the signal this one also don't look at it. We have the signal propagation, right? What we have is the speed of light multiplied by T2 minus T1. And it's also the same as, because they are using the same distance, it's also the same, but this time is T4 minus T3, right? Yeah, it's looking like this. And yeah, what we have is looking like this. And what we do is that we further to combine these two information. Let me see. Yeah, we're going to combine these two. So we're going to combine these two equations together. So what we have is on the left-hand side, we have 2 times of the range. And that one we have C. And inside we will have T4 plus T2 minus T3. And we also minus T1. And T2 and T3 is actually having some relationship. Is the processing time on our station. So actually in here, we'll have the T4 plus our processing time, which is in here is for example, it's assumed to be like this one of seconds, and then we divide it by this one. No, it's actually, let me see, because T3 is larger, so that it should be minus. Yeah, it should be minus. And looking like this. So what we get is actually pretty much the same as this one. We have T4 multiplied by T1 is the total time on our aircraft. So the timing is actually only on our aircraft. The clock, we only need to use the clock on our aircraft is okay, because T2 and T3 is already eliminated with each other, and they only have the difference time is regulated. That the process time is regulated, then it's already okay. So the idea is that, the very important idea is that they only need the clock on our aircraft. They do not need any clock information, direct clock information on our station, because they regulated the process time as this, so that they do not need any clock information in here. So that it's actually a very good example for this ground station. If the clock is not very good, we can also not very affected to us. So that's the problem. And we have our localizer. In the later part, this part is related to ILS. So for ILS is that if our aircraft, we have two kind of beams loops in here. So what we measured our aircraft location is that based on the strings in here, it's looking like this. So if we are going into this one, is a bit difference with our center of our runway. So we have we receive more on the top loop and receive less on the lower loop. So that's the idea. So for the guys part or guys loop, it's also the same. We have two loops. We receive the upper much more and the lower less if we are going to be on the top. And for this, we'll have more on this one and less on this one. And yeah, if we are less on the ground, so we will receive more intense power on the lower one. So that's the idea. So another part that you need to also remember is that you need to know how to read those indicators. So what's important is this kind of indicator. It shows how you're going to make use this iOS system. So during your landing or during your flight, you have the VOR and you also have this iOS. So what they give you is like you have an instrument, and then you have lines. Yeah, not looking like this. It's like instrument, and you inside the instrument you have the cross, which is the reference, and then you have lines looking like this, or you're looking like other lines. If it is not in the center, it means you are already deviated. And what you do is that you need to follow the line. You are go with the line's direction. For example, the line is on your left-hand side, you make your aircraft go into left-hand side. So let's look at this example. You have this line. So what you do is follow the line. This the vertical line is related to the localizer, and that one you need to make sure you need to trim your aircraft to the correct direction, and you need to move to the right. And the horizontal one is from the guide slope, which is making you have a correct descent to it. So you need to make it going down your aircraft, and that's the idea. So this needs to be, you need to very clear about the direction of how your maneuver needs to be done when you are going to make sure finally they will be aligned to the cross reference. Yeah. And yeah, let me see. So how about let's have like few minutes breaks, like 10 minutes of breaks. So later on, I will have two more examples of the later parts, and we are going to, yeah, so that's it. So actually, do any of you know that when is your examination of this lecture? Do you already know? You know, right? So it's actually very early. So actually, I already made up the exam paper. So in the final lecture, I will talk about some highlights, some parts of this lecture that may be contained in our examinations. Yeah, in our tutorial 3. And I will later announce you with the location of tutorial 3 and the time. Okay, so let's go back into today's tutorial. So this one, yes, great. So some of you may kind of like confused why we are using addition or minus. We do this dB calculation. So let me use an example. Is we are location A, and what we have is that we have some kind of gain in the first part, so that after this gain, we'll get B. And after that, we're also going to have some kind of propagation, and we have another gain. And then what we get is after that, we'll have C at this part. So we wish to calculate the ratio of the power in terms of this transmission, in terms A and C. So let's look at how it works during the propagation. If we're going to see how much power being increased or being reduced during the propagation, what we have is that we compare A and B, right? What we compare is A and no, we actually in the end is first, we're going to compare B with A. And because they usually compare in dB, so what they do is that they will have log with 10 with this inside, and in the beginning we'll have 10 plus with it. So this is their comparison in terms of dB, right? And after that, we'll have another part of the propagation. In here, we are going also to have this kind of similar comparison. It's looking like this, right? In terms of C compared to B. This one, right? And this one will have this gain. Let's say, for example, this gain is equals to 2.1, and another part is gain equals to 2.1. I'm talking about let's get rid of the loss in here. Let's get rid of the loss of power in here, so that we have these two parts. So if we're going to compare with the power that from between two ends, let's say between two ends, so what we have is the log. We need to see the log from C to A, right? From C to A. So what we have is that we can make this log 10, also have 10 on top of it. So what we can do is that we're going to put this equation. We have C divided by B and multiplied by B divided by A. This one, we do this trick. So one is in the denominator, one is in the top of it. So for this one, because we are doing log operation, so what we can have is actually we're going to separate these two. And what we have is like 10 log 10 and to this one, because it's multiplication inside the brackets. So what we have is addition to this one, log to B to A, this one. So it becomes looking like this. So actually, that's why if you are going to operate something in terms of dB, in terms of comparison, the operation in here is also addition in here, because the change is inside here, is inside the log is multiplication. So if it is going to be put outside the log, it will be addition or minus between different terms. So that's the reason why it works like this. And let's go back into the surveillance system. So for the surveillance system, is actually not pretty much of the knowledge of that. Lots of not that many of the calculation of that. The main one is related to PSR, the range, and this one is the operation is very similar. You have 1 plus from our station, and it's going to be reflected by our aircraft. So the key word is that you have the reflection of the same signal. So this reflection do not need any process time. It directly, instantly being reflected of it. So what you calculated is directly. You measure the time in here. The clock, you have the clock in here. You have a timer in here, and you directly measure like T1 receive propagates and receive at T2. What you receive is like T2 minus T1 divided by C is the speed of light, and then you will directly obtain it. No, it's multiplied by C. So you directly obtain with the distance. Okay, so that's very straightforward, but that of course you will have some design problem because your plus in here is not only generate once, it will periodically generate the plus. And the problem is that if your aircraft or other objects is too far away, that the first pass is going to be attached to the aircraft, it already may emit the second pass. So that when you receive some pass back going feedback to you, you're not sure it's coming from the first pass or the second pass. So they have some this kind of, we call it ambiguity in there. And because of that, you don't know which one is that, and you do not know the distance to be calculated by the first one as reference or the second one as reference. So the example is look like this. If we're going to receive the pass looking like this, we're not sure it's coming from the very closer one or the very beginning one. We're not sure if that because its power is highly attenuated. The power is very weak compared to the normal value. It's very weak, so that we're not sure it's really this one or is really this one. So that's for this one, we will have this case. So they actually comes with a limitation for our devices. The PSS, they have this kind of like limitation of the range related to the period, how periodically generate this signal. If your signals, this pulse generation is too tight, let's say let's change, if they are too tight, what will happen is that you are very hard to detect any of the signal, because if what you can distinguish is the very close one. It's really hard to do so. And if let's say if they are far away, their pulse is far away, so you can have a longer time to receive from the same signal. So the ability of detection on range will be increased because you have a longer gap to receive the signal. Yeah, so that's all. That's this kind of effect. So based on it, we can actually calculate it, the limitation, how it looks like. So we can have this kind of question that to calculate the maximum range of a radar based on the information. For example, how to design a radar to achieve a goal to detect this maximum range of the user or the aircraft. For example, we have the requirement looking like this. Let's clear it. We have the requirement looking like this. We need our radar to be detect 170 kilometers to do this one. So what we can do is that we wish to know, we wish to detect this one, and we know that this is related to how much periodic the signal is going to be generated. And it's also related to the time. And what we do is that we need to firstly know how long our signal will be propagated, because in before, this is how long the signal will be propagated. This one is how long they will be propagated. And if they are longer, then they will be propagated longer. It's a longer propagation signal can be fit into a longer gap in between. So we need to calculate that. So what we do is that we have 100 kilometer. This is only for one way. We need to multiply by 2 because we have the one way to go and feedback to our station. And so that the total signal traveling length is looking like this one. And this traveling length needs to be needs to be adapted to be maintained within one gap of 2 pulses. So what we have is that the difference in time. So in this difference of time, we will have make this number to put into here. So what we need is that also we need to calculate it of it. So what to calculate it is like, let's see, we'll have the distance, and then we will going to be this distance, and we know our signal is traveling by speed of light, and we want to calculate the difference, how much time we need to travel this signal, so that we have 3 for this one, but because it's kilometer, we have 1000 in here, and divided by 3 multiplied by 10 to the order of 8, we have the speed of light. And after that, we know our the time we need to travel for our signal. So what we got is, if you have calculator, you calculate it as 1.133, but this one is for millisecond. Yeah, this is for millisecond to this. So you need to, you only have 1.133 millisecond of time to receive the signal in this gap, which means this gap is what you need is to have 1.33 millisecond. So that is that if you only if you reach this length, then you are able to receive that kind of length of the aircraft in range. So that you need to reach this. So this is the limitation of this gap. But in this problem, we are going to talk about this one is PRR is related to the frequency. So this one is related to the frequency, so that we need to make time into frequency. To do so is actually 1 divided by this one. So it's actually 1 divided by this one. But this is millisecond, right? So this is to the order of -3. So what we got is calculated is 800 something 0.6. And this one is in terms of frequency, but this one is in terms of, because we are talking about the frequency of pulse, so the unit will be pulse per second. So this one will be pulse per second. How much pulse will be generated on each second? So that's this kind of unit. So this is very similar to Hertz. That is very similar to Hertz, but it's in terms of calculating how much pulse will be generated on each second. So that's how we're going to be calculated this. And we'll also have the detailed equations and the process we'll be writing on this. And after that, we'll also talk about some SSR, the secondary surveillance radar. And that one, you need to notice that the propagation pulse, the characteristic is the signal is generated from the ground station. And it's going to be received by our aircraft. And on the aircraft, we will also need have some kind of time to process the signal and also to change the frequency. And then it's going to be feedback to here. But for our aircraft transmitter, we do not know the direction, the location of our ground station. So this one is going to be an omnidirectional propagation. So you see, we have a lot of circle, and this one is to make sure, although you do not know the location of the station, but you can still receive the signal because it's omnidirectional. Because of this omnidirectional, of course, it will have some kind of problem, right? For example, other stations that do not want this signal, but also receive this kind of signal, or other effects like other interference. So that's also some kind of problem you need to remember. And of course, the signal they're going to be transmit is with like mode A and other kind of, like, for example, newest mode S or others. And they will have this kind of rules and to embed with it. So we can look at an example of this, is that they actually based on different keyings. So how to read this is that this is the real signal. This picture is the real signal. But the real signal, each part has their own box, and their box on the signal is being like being exchanged with each other. They are not aligned with each other. So when you are going to read the information, for example, you need to have the first information. You need to have the box of A4, A2, A1 related to the first information. You need to collect this information from different sections of the signal. So A4 is in here. A2 is in here. A1 is in here. So need to collect the information from different boxes and to combine to the original information. So let's look at the example in here. So what we have is like this kind of signal. If you have all information on different box, and if let's say this one is the real transmit signal, and what we have, the information is 1 and 0. So we look at which boxes will contain 1 and 0. And we look at here, we see A1 is containing 1 for this signal. A1 is containing 1, and B2 is going to contain also 1 for this case. So we only have 2 numbers. So let's see, look at how this sentence look like. So the whole sentence is look like A4, A2, A1, B4, B2, B1, and so on. So others we do not care because they are all 0. They do not contain anything. And we're going to look at this number. So A1 has something. So we put A1 as 1. B2 has something. And we also put 1 in B2. So then we fill with others with numbers. And we got this one. So we're going to understand how to read this one. And because they are using those kind of like a binary data, and we're going to read this one in binary data, is that in the corresponding to A4 is 2 to the order of 2. In terms of A2 is 2 to the order of 1. And in terms of A1 is 2 to the order of 0. So in terms of binary data, they usually the lowest one, the lowest box is related to 2 to the order of 0. So that it related to the number 1. So for this 3 bits, we're going to read it will become, this one will become 1. And for the second one, only have the bits on the second one, which is the 2 to the order of 1. Other one is 2 to the order of 2 and 2 to the order of 0. They are all 0, so they do not have any information. So this one, we read it as 2. So we combine with other boxes is actually 0, actually also 0. So what we have is 1, 2, 0, 0. So this is the number we're going to have. So that's the data we're going to contain in this mode A signal. So how to read it. So for example, others, you can also use the same techniques, same way to read this signal. Yeah, for example, 1, 2, 3, 4 is also the same. Yeah. Let's try again for C1, that 1, 2, 3, 4. So this one we got C1, and the other one is C2. We also have is D4, right? So what we have is C1, C2. So if we are going to have C1, C2 is using the on top one. Let's see, this is C1, C4, C2, C1, that one. So we have these two have numbers. So if you read it in binary, this is 3, right? And for the D, we have D4, D2, D1, and only have D4 have information, and others are 0, 0. And for D4 is actually related to number 4. So the total number is 1, 2, 3, 4 for this one. So that's actually straightforward. And this is how we read it. So in the last lecture of our subject, we talked about the avionics system integration. And this part, we mainly talk about how to read some like data using the format of the of the air ink 429. And what we have is that they actually encode using this kind of signal properties, bipolar, return to 0. And for this one, it use always return to 0 to indicate any of the signal. So if you are going to have representing 0, which is related to minus 10 volts, so it will have a certain period going down into minus 10 volts, but it will eventually going back into 0, no matter what happens. And for the another kind of signal, let's say, for example, if you're going to indicate 1, and what you have is to increase the voltage into positive 10 to know that you're actually going to transmit 1 in here. But in the end, it will going back into 0 eventually. So, but for the another type is no, so that will always keep in 0 voltage. So that's all how it's going to be collect this data. And this now, if this one is going to be always keep in 0 for 4 bits, it means that the beginning of the signal. So after these 4 bits, it will begin with another signal information. So that's how it looks like. And then we also need to know how the structure looks like, and how to read the structure and know how to signal what the information is contained with it. So let's because this one is very close to you, I will fastly go with it. The label is actually in the first 8 bits, and the SDI, which is the label is related to the which information is going to be transmitted, and the source destination identifier. So that one is related to SDI, is on 9 and 10. So this one is related to the definition of your system. So this is very related to the definition of your system. So different system will have different their definitions. So it's very depends on the documentation. And but for the data, they will have a certain format. So it will, like, two usual way is like BNR and BCD. The difference is that BNR is going to be directly read the binary value. So in here, we actually have data is from 11 to 29, right? We actually have, what we have is like we have 19 boxes. 19 boxes. So these 19 boxes, we're going to fully indicate binary data, which means that you have the number from 2 to the order of 0 to 2 to the order of 18, because you have 90 boxes, right? So that's it. That's the range it can able to be indicate. And for BCD, we will be a bit different. It's like it's going to be separate into different parts. And for 11 to 29, it will be separated with 4, 4, 4, 4, and 3. So this one is it will be separated into 5 region, 5 parts, 5 boxes, and each one will contain 4 smaller boxes to contain 1 on 0. So let's look at it. So each one of the boxes, the ability is 2 to the 0 to 2 to the order of 3. No, let me see. Yeah, 2 to the order of 3. Yeah. So let's go back into 8. No, let me see. 2 to the order of 3. Yeah, 2 to the order of 1, 2 to the order of 2 to the order of 3. So actually, if you're going to also use other numbers, this one is 8, right? You can also use other numbers. This is 4, this is 1, this is 1, this is 2. So you add up together, you are able to represent 16 things together, right? But you need to have you have 16 things. So this one is able already enough for you to evaluate something related to 0 to 9. Is able to do so. So that's why it used 4 boxes to do so. Yeah, The other one is a signal status matrix. This one is related to the, as it says, is related to the status of the matrix, the signal. So for example, some of the indications, they may relate it to whether the signal is good or not, or some information related to the signal is related to the label of it. We'll see it later. And the parity check is an indicator to make sure your signal do not have any error. So what you need to remember is that this kind of ARINC 429 is always using odd parity. If your signal, all the boxes combined together, add up together, they are odd number, it is a correct signal. If this is becoming an even number, so during the propagation, one of the box have some problem. They flip from 0 to 1 or from 1 to 0. So the signal itself, the information itself is incorrect during something wrong in the propagation. So here is usually what you have is a data specification, is that what you need to read in this table is a correspondence between different parameters and the corresponding label codes. So for example, if your code looking like this, then after that, those in the data boxes, they are related to the oil quantity, this one. And they are using the code. The format is using BNR because in here we have a small cross. So if you are having another pattern looking like this, they are related to the carbon compartment temperature. And they are using this one. The data is using this format, the BNR format. And we can directly go into another questions example of this. So let me do a tricky way, is that we're going to represent this kind of information, and then we're going to write the corresponding ARINC code. Let's do it. So if we are going to transmit some information related to 27,504 nautical mile in DME distance, and is formed in BCD. So how we can do this? So firstly, we look at this one. We need to transmit DME distance, right? So we look back into the table, and we see here we have DME distance, and it has two different kind of DME distance, but one is in BCD, the other is in BNR. And we look back again, we use BCD. So we use BCD at this one. So what we need has 1, 0, 0, 0, 0, 1. So that's in here, we need to put in 1, 0, 0, 0, 0, 0, 0, 1, so that they are consistent. So this one is going to show DME distance in BCD. Yes. And then after that, SDI is usually defined by other, like your documentation. So I will directly give this number. And then we need to look at how we're going to put those data in here, right? And we see we are using BCD. So this data is also following the BCD format. So we need to separate it into 4 boxes, and finally we have the last one is 3 boxes. So what we need to do so is to put into different kinds of 4 boxes. This one, and 1, 2, 3, 4 boxes. The last one is 3 boxes. So we're using this to represent. So this the first boxes need to be represented by 4, 0, 5, 7, and 2. Yeah, we need to use these different boxes to representing this number, right? So let's do it. So for the beginning, we use 4. So for different boxes, the meaning is that is 2 to the order of 0, 2 to the order of 1, 2 to the order of 2, 2 to the order of 3, so that our representation need to be 4. So it should be 1 of this one and 0 of this one, 0 of other ones. So that is 0, 1, 0, 0. And for the second big boxes, it's all 0 because we are showing 0. And the other one is 5. So that we have 2 to the order of 3, 2 to the order of 1, 2 to the order of 0. So for 5, is that equals to 4 plus 1. It's equals to 4 plus 1. So it's equals to this one at this one. So the others will be 0. So what we have is 0, 1, 0, 1. And we have 7. So for the 7 one, it's also very simple. It's this, we use the same way, and it's equals to 4 plus 2 plus 1. So that we put into the number, we have 1, 1, 1, and 0 for this one. So we have 7, and we have 0, we have 1, we have another 1, and another 1. And for 2 is also the same. But this one, we only have 3 boxes, right? Yeah, so the beginning one is 2 to the order of 2. The second one is 2 to the order of 1. And the last one is 2 to the order of 0. And 2 is equals to 2 only, and only the middle one have the number. It's okay. So what we get is 0, 1, 0, right? We already have this kind of number. And then we have the SSM need to take care. So this one is related to form. So we're going to look back into the table. So if it is 0 and 0, if it is 0 and 0, it related to plus, north, east, right, or 2 or above. They are not related to us. And for the second one is no computed data, so something wrong, but we not wish to emphasize that. And the third one is related to functional test. We are not testing anything. And the last one is 1, 1 and related to minus, sounds, west, less, from. This is what we need and below. So from is what we need, so that in here we wish to put 1 and 1 in here, right? So that's one. And the last one is to determine parity. We need to make this information, it should be correct, right? Because we need to transmit this information. So for a correct transmission, we need to ensure the summation of them should be odd number. So let's count. We have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 of 1. So it's 11 is odd number. So this one, we need to make the total number to be odd number. So this one can be 0. So the summation with 0 is still 11. So it's an odd number. So this is how we get this line of the airing signals and the boxes in here. So yes, so that's how it's. So let's put back in here. So that's the result of it. So based on this one, you can also write back into the signal in here. You can also, based on this code, write the signal back in here based on this, like the up of the voltage or down of the voltage. But you need to know is that the sequence will be a bit flipped. You see, here is starting from 1, 2, 3, 4, 5, and something like that. So that's the, if you're going to draw how it looks like the signal, you need to make sure that. So that's the case of it. So that's basically how all the things works. So actually in the last part of the lecture is not so many of the calculation. So the calculation in this subject are basically more on the in the beginning, week 1 to week 5. So they related to aerodynamics and some controls, especially some like air data and also the INS, like inertial navigation sensors. They are very important. Okay, so that's today's tutorial. So I will leave, I will let the last few like half hour to staying in here. So if you have any questions, you can ask me at that time. Yeah. So thank you for today's. Oh, let me remind something. So starting from next week, we are going to have case study. So make sure everyone's presentation, before you present something, you need to make sure you show me your name and also your student ID so that you know who is presenting something so that we can do the grading. Yeah, thank you.